Welcome, everybody. I'd like to introduce Aiichiro Nakano from USC, and he's been doing large-scale computing for physics and multiscale processes, incorporating AI in it. Yeah, welcome, Aiichiro.
Thank you, Greg. So I share my screen, right?
Yes, absolutely. Thank you.
So this let me see. The first time, okay, in test, first time I'm using Google Meet.
I see. So you might have to give permissions. That's the one thing. Oh, beautiful.
Am I sharing my screen?
That's perfect.
Okay, so can I get started?
Yes, please.
Okay, so the first, I'd like to thank Greg for the kind invitation to this very exciting alphabet modeling talk series. I looked at the previous talks and then I already learned a lot from them. So today, I will talk about the multiscale light matter dynamics at the high-performance computing crossroads. So I will explain what it is, but it's about the paradigm shift in scientific computing. And so this work was done in collaboration with my colleagues at USC, and then also Argonne National Lab, Intel, and then Boris Kozinski's group at Harvard, and then Professor Shimojo's group at Kumamoto University, Japan, and then Sony. So let me get started. The first, I want to emphasize that the computing landscape for science is changing very rapidly. First of all, the current exascale computing architecture is not scalable into future. As a result, we are witnessing a so-called compute Cambrian explosion, where diverse computing species are emerging and then competing. At the same time, quantum computer has outperformed the fastest classical supercomputer, as represented by this Google's effort, which is one of the the corresponding author is the Nobel Prize in Physics laureate this year. The meantime, AI is everywhere in science and engineering. So we want to use all of this advancement to develop advanced science. So at this nexus of post-exascale computing and quantum computing and AI, what we want to do is this: molecular dynamics and machine learning. First of all, molecular dynamics follow the trajectory of all the atoms to study material properties. On the other hand, non-adiabatic quantum molecular dynamics explicitly treat the motion of this electronic wave function, which can be excited by light and then photon. The most recent advancement in this area is first principle-based neural network quantum molecular dynamics, in which these electronic wave functions are replaced by a deep neural network to describe quantum mechanical accuracy in a fraction of computational cost. So we do molecular dynamics and machine learning at the exascale. When the US Department of Energy designed a current Exaflop computer, and then they publish a white paper. And then on the cover of the white paper, there are 4 simulation images, and then 2 are from our group. First of all, this central image, and this is our 17,000 atom quantum molecular dynamics simulation to study hydrogen production from water using lithium aluminum, the nanoparticle. In this movie, red are lithium atoms, and silver is the charge density around aluminum atoms. And then these green bubbles are produced H2 hydrogen molecules. And then for the clarity of presentation, we are not showing that a lot of water molecules surrounding. And this left image is the billion atom chemically reactive molecular dynamic simulation. And then let me see if I can play this. So here we are studying the collapse of so-called cavitation bubble. And then ultrasound, you can create a bubble in water. And then when the bubble collapses, and that create a nanojet or shock wave. So this collapse is creating the nanojet. And this nanojet is hitting the solid surface in this case, silica, to chemically and then mechanically damage the surface. So here, this nanojet is represented by a streamline, just like a computational fluid dynamics. So bottom line is that once we have billion atoms, we can do fluid dynamics atom by atom. That's the first multiscale. But today, what I want to talk about is quantum molecular dynamics. The quantum molecular dynamics, or QMD, follow the trajectory of all the atoms, whereas the interatomic interaction is computed quantum mechanically from first principles. The most widely used quantum mechanical simulation method is called density functional theory, for which Walter Kohn received 1998 Nobel Chemistry Prize. So in short, density functional theory reduced the exponential complexity of the quantum many n-body problem to order n cube by solving n number of one electron problems self-consistently, instead of directly solving one n electron problem, which is exponentially complex. So for computer scientists, this is a complexity reduction. Still, this order n cube complexity limits the problem size to be a few hundred atoms practically to simulate larger systems. And then many so-called order n linear scaling DFT algorithms have been designed. And all these algorithms are based on the so-called quantum nearsightedness principle promoted by Walter Kohn, and which is the physical data locality principle. Data locality is another important computer science concept. So the quantum molecular dynamics I just described is called the adiabatic quantum molecular dynamics, in which electrons stay in their ground state. And then this adiabatic quantum molecular dynamics is based on the so-called Born-Oppenheimer approximation. And if you watch the movie Oppenheimer, there was a scene that young Robert Oppenheimer was giving a seminar in front of the Werner Heisenberg, the founder of the quantum mechanics. And then in that seminar, the Robert was presenting this paper with Max Born, and then in which Born-Oppenheimer approximation was derived. That's what we are doing in adiabatic QMD. Actually, the origin of quantum mechanics and supercomputing, that's what we do, is the Manhattan Project in 1945 at the Los Alamos. Since this kind of dark origin, electrons and then atoms went through a long, long journey. And now we are using that to study kind of like generate clean energy from light and then so on. So last year, a very talented choreography, Pei White, created the dance performance. So here, inspired by our quantum mechanics and supercomputing research. So here, this Araya is playing electron, and here is playing electron, the atom. And then it's a beautiful kind of interpretation of that quantum mechanics and supercomputing by artists. So we go actually beyond Born-Oppenheimer. That's the topic of today's seminar. So
here's a question, just to set the ground for the kind of dynamics you're modeling. I guess what regularities are these approximations taking advantage of that make the computation simpler?
Adiabatic molecular dynamics. So basically, like an electron is light, so moves so fast. So for electron, that the atoms move like so slow. it's like an electron is a hummingbird. For them, the atoms are like a elephant. So no matter how that elephant move, electron can just instantaneously follow that its movement. So that's adiabatic. But once you shine light, light is also fast. So we cannot stay in that Born-Oppenheimer adiabatic. So that's why to study interaction with light matter dynamics, we need to do this non-adiabatic quantum molecular dynamics, in which electrons, and we cannot assume that the electrons stay in the ground state.
Okay, so the idea, the change is because light moves much faster than the electrons, you have to go through the state change as well, energy level transitions because of the light interaction, and you get to see those transitions over time. So the old approximation doesn't work anymore.
Yeah, so that's correct.
Got it.
Yeah, so in this non-adiabatic quantum molecular dynamics, we follow the photo-excitation dynamics involving electronic wave function and then atoms. So we have been doing this for many systems. And then in this the series of publication, the left movie is so-called a light harvesting molecule. So the top is the photo antenna, and then absorb the photon and then creating electron, so-called a Hall pair, and that go to the bottom, so-called a chemical reaction center. So this is basically what the plant is creating that energy from photosynthesis, and then we are studying that kind of thing with non-adiabatic quantum molecular dynamics. The right movie is actually organic solar cell, and then the shine of light create so-called electron, and then leftover electron is called the Hall, positively charged. So this pair separate and then create electricity. So that's the solar cell we are studying. So that's a non-adiabatic QMD in a nutshell. The more exciting application is so-called the attosecond light matter dynamics, which was the topic of the Nobel Physics Prize in 2023. So attosecond here means 10 to the power minus 18 seconds. It's very fast. So why this is exciting is that attosecond physics could revolutionize information technology by enabling ultrafast computing and sensing devices. People are already talking about the petahertz electronics, which is 1 million times faster than the current gigahertz CMOS technology. So to study such light matter dynamics in quantum molecular dynamics, we needed to develop a new kind of non-adiabatic QMD, in which we call the DC-MESH or divide and conquer, Maxwell-Ehrenfest and surface hopping approach. And then DC-MESH consists of two parts. First, local field dynamics solves Maxwell equation for light, and so-called real-time, time-dependent density functional theory equation for electron to describe the light matter interaction at the short time, like attosecond. And this approach is called the Maxwell-Ehrenfest approach. And then, in addition, the quantum excitation molecular dynamics, or QXMD, describe non-adiabatic coupling of excited electron and then atomic motions based on so-called surface hopping approach. So this is a slightly longer time. And then handshaking between this, the fast local field dynamics and then a little slower quantum excited molecular dynamics take place by so-called electronic occupation number. Each orbital is either occupied 1 or unoccupied 0 or partially occupied in between. And then here, this minimizes the GPU, CPU data transfer. The reason is that the local field dynamics fit very nicely to GPU, so it is sitting there. On the other hand, QXMD is sitting on CPU. So this handshaking, we call the shadow dynamics, that minimize the CPU, GPU data transfer. I'm going to explain this more in detail later. So in order to deploy this DC-MESH non-adiabatic QMD on VR Exaflop computer, we have several DOE computing grant, and then under Aurora early science program. And we are one of the initial simulation user of the two exaflop spherical and then measured flop performance 1.01 exaflop Intel Aurora. So exaflop means 10 to the power 18 floating point operation per second. But there's a problem. Namely, high performance computing is at a historic crossroad where traditional modeling and then simulation application may not survive. So we are in an existential crisis. This is because computers are increasing more heterogeneous by integrating different functional unit or chiplet, and also focusing on low pressure arithmetic to serve market-dominating AI application. First of all, to begin with, the application have to be a general matrix multiply or GEM to get any performance benefit. In addition, we need to take advantage of the low precision like single precision, half precision, or even 8-bit to get the high flops performance. So now our application scientists now joke that to survive, the question is to gem or not to gem. So in addition to this problem, low precision problem, the light matter dynamics is a very challenging multiscale multiphysics problem, which involved multiple field and then particle equation of different computational characteristics for light, electron, and then atom, which extends over like electron and then atom spatial-temporal scales to device level spatial-temporal scale. So now we face this multiscale, multiphysics, heterogeneity, and low precision challenge. So actually, there's a trade-off between arithmetic precision and the flops performance. And this year's Gordon Bell Prize finalist is called the Nobel Prize of supercomputing. The three of them actually highlight the dramatic effect of floating point and brain float precision on the flops performance on the Aurora supercomputer. First, traditional simulation based on floating point 64-bit precision by Zhang et al. And then my colleague at USC achieved 0.7 exaflops on nearly full Aurora. On the other hand, machine learning application based on hybrid FP32 and then BF16 precision achieve just astonishing 10 exaflop on the full Aurora. So there's a dichotomy between simulation and the machine learning. If you do machine learning, it's okay, but if you do simulation, you are doomed. So our own Gordon Bell finalist paper by my student, Taufik Razak et al. We use a hybrid FP64, FP32, and then BF16 precision to get a scientific result for simulation. So that's basically we are breaking the simulation machine learning dichotomy on the supercomputer.
So let me understand this, because this is a big, okay, so first of all, I've never actually heard of brain float. So it is where you can do big numbers, but without much precision, right?
That's right, more dynamic range, but less precision. But somehow the machine learning people prefer BF16. So actually, like maybe at the end, I'll talk about this kind of like precision engineering.
Right. And so what about a given problem makes one, well, number format or whether it's floating or fixed point preferable or usable?
So what happened is it's all becoming that problem dependent. So now scientists need to care, like not like a given 64, 32. The application scientists need to decide by looking at the problem, I need 48-bit or I need a 20-bit. And then now there's something called the GEM emulator, like Ozaki's method, already implemented NVIDIA. So you can choose, user can choose my application needs precisely this bit. So I actually like the precision is a resource. So like scientists
Right.
have to be smart to choose the right precision.
Interesting. Yeah, Ravi?
Any question? More question?
Yeah, Ravi has a question.
Oh, okay. Please.
Please hand this up. Or maybe we'll wait for him. And just one more, if you had dynamic changing in precision, is that a usable thing? Like, as you say, it's a resource. So there's like using memory, using compute, that's a resource. But precision doesn't seem like a dynamic quantity, or is it now?
That's right. For now, that our approach is a static. So what happened is for given problem, like a which material, and then what light frequency, and that all change. So right now, that one simulation take like a week on the supercomputer. So for that, during that time is static. So our program written is C++ with the class template. So the precision is parameterized. Right now, the 643216, but actually, I will tell you later, Aurora has even more control over the precision.
Right.
So it's become more fine-grained that the tuning is possible. So that's a kind of like a hardware, software kind of co-design. I think it's kind of coming now.
Yeah, and so and Ravi's question was, in your ARIS approach, is the trade-off for different precisions? I mean, because is the trade-off lower precision, so higher performance, lower precision of the final results?
Right. So what happened is that we choose the application such that this precision we use is the good enough, but we didn't kind of pursue like a more optimization of the bit engineering. We just use that existing this 643216.
Got it. Thank you very much.
Yeah, thank you. Yeah, that's the real essential question, right? So actually, the things are getting worse. So we recently got the award, early access to this the next generation at the supercomputer at the NERSC, the Berkeley, and this is called the Doduna. Doduna is based on the NVIDIA Vera CPU, and then NVIDIA Rubin GPU. And I look at the announcement by this the Jason Huang on Rubin. It's kind of scared. So now that Jason is promoting FP4 clock performance. FP4 is what? 0 to 15, and then what science we can do, traditional science. So that's really like this the existence crisis. So so there's the problem. Then we solve that multiscale, multiphysics, heterogeneity, and then low precision challenge by harnessing heterogeneity and then low precision arithmetic, I think for the first time for simulation. So first, our divide and conquer recombine algorithm divide a problem into not only spatial, that's the traditional divide conquer combine, but the recombine means not only spatial, but also physical subproblem of different computational characteristic, and then which are then solved using appropriate method on best matching hardware unit before we combine into the total solution. In addition, our metamodel-space-algebra lets subproblems to reside in respective hardware unit like a CPU or GPU, while minimizing communication and precision requirement. So that's the kind of precision engineering. So together, the DCR and then the MSA delineate subproblems with small dynamic range and the minimal mutual information. These are the two keywords important, using parameterized precision, which map well onto AI accelerators that support a spectrum of hybrid precision method. For example, Aurora allows either 1 or 2 or 3 BF16 gems to be accumulated in FP32 to provide varying precision and speed. So, so that kind of spectrum of accuracy is now being provided by hardware. So this create meta-scalable algorithm hardware co-design opportunity in the post-exascale era. So meta-scalable, I mean, design algorithm only once, and then which will continue to scale to future architectures. So based on this divide and conquer recombine and the metamodel space algebra paradigm, we have developed multiscale light matter dynamics software. In this MLMD software, the spatiotemporal scales of first principle non-adiabatic quantum molecular dynamics are boosted by AI-accelerated excited-state neural network quantum molecular dynamics. So, MLMD software consists of a DC-MESH module for non-adiabatic quantum molecular dynamics and excited-state neural network quantum molecular dynamics module, 2 modules. And so, last year's both Nobel Physics and Chemistry prizes basically heralded the new era where AI is embedded in the very fabric of science. So Google people must be very, very familiar with the Nobel Chemistry Prize to Google DeepMind. So this is our application is another example for that. So a little more detail. The first level of divide-conquer-recombine is the spatial divide and conquer density functional theory. So in the divide and conquer density functional theory, the total space omega is the union of overlapping spatially localized domain omega alpha, like here. Within each domain, we solve so-called Quantum equation to obtain local electronic or quantum wave function. But here, the so-called Hamiltonian operator operating on this local wave function, depend on the global potential, which depend on the global density, electron density. And then global density in turn is the sum of local density. And local density is the sum of the local quantum wave function. So, so this is a self-consistency. So we determine the local electronic or quantum wave function and then global potential in the so-called the global local self-consistent field kind of fixed point iteration. That's the order F. And then here, our so-called globally scalable and then locally first electronic solver combine real space multigrid method to represent to solve the global potential problem, and then plane wave basis cosine and then sine to represent local wave function. So our hybrid electronic solver combined scalable multigrid tree-based method for inter-domain computation, and then fast Fourier transform for intra-domain computation. And more recently, we even designed something called a globally sparse yet locally dense eigensolver, and then which convert the sparse matrix like this by row and then column permutation into a union of dense matrices, which can be operated with GEM.
So question, by Ravi, there's a concern in DCR that the cost of the divide reduces the performance gain. I guess he's talking about the communication cost of recombination. Do you see that?
So the communication cost, so this is the divide and conquer part. So so we want to locally take advantage of the GPU, that's the dense computation, but the global interaction, you want to be very sparse. So like the network cost is a minimum. So the best is the tree-based divide and conquer. So that's what we do, this globally sparse yet locally dense, and you get even like tens of thousands of like that network connected computer, we can get nearly 100% scalability along with high props with the locally dense part.
And I think what is critical about this thing, this is not molecular dynamics you're dealing with, because I'm seeing like a giant hierarchically dense linear solver, right? Like a multigrid here, not free body motion kind of a problem in this stage. Is that fair?
Yeah, that's fair. So what happened is that's where why we can do order and quantum mechanics is that there's a physical data locality principle called a quantum nearsightedness. Electrons are nearsighted. So this the 3-body, 4-body, like or more exponential entanglement is so short-sighted. It cannot extend more than 3-4 atoms. So all these things are kind of taking care of the physical data locality.
That makes sense. Yeah, and the boat, do you have a question?
Oh,
yeah, I see already answered it. Locally coupled.
Yeah.
Larry.
Oh, okay, okay.
Yeah. In fact, actually, I'm noticing this is very similar to like a universal simulation, which is gravitationally based, but most of the dynamics are highly local because gravity is mostly local, and long distance interactions are can be approximated very effectively.
So this is better than that gravity, because the material has the positively charged nucleus and negatively charged electrons, so like they are screened out. So from outside it looks like a neutron, so that there's no long range interaction. So
I'm sorry. Yeah, you're right. So gravity, you can aggregate long distance interactions. Here, you can ignore long distance interactions. It's better.
But you're right. That I have a colleague at the last slide. I will talk about this gravitational problem, and then we can still do a very similar thing.
Interesting. All right. Yeah. Thank you very much.
Yeah. Thank you. So on parallel computer, we divide the computation into those of domains, and then so that's the trivial. But for higher parallelism, even without each domain, we use so-called band parallelism and then domain parallelism, hierarchical domain. So we call the band, space, and domain BSD decomposition. So the second level of the divide-conquer-recombine is the physical divide. So this is called the local field dynamics and quantum excitation molecular dynamics decomposition. So first, in local field dynamics, fine level partial differential equation for light and electrons are data parallel and then fit naturally to hardware accelerator such as GPU. So that means every single differential operator based on that nearest neighbor, like a spatial point, like a Laplacian operator. And then that's uniform for all across. So that's a data parallel. So that fit naturally to GPU here. And then on the other hand, the complex chemical interaction in QXMD in coarse electron atom description can take advantage of complex instruction set in the CPU so that the QXMD sit on the CPU. And then this is the first level of the metamodel-space-algebra called the shadow dynamics. So GPU resident proxy, the LFD, that means how that the light eventually affect the long time kind of electronic excitation and then atom motion. That proxy captured effective action of LFD on QXMD through minimum information, namely very small change delta F of electronic open number F. So that itself is already small dynamic range. Like so small change by light is even more small dynamic range. Therefore, we afford that the low precision arithmetic, like a 32-bit. So actually, the similar mixed precision electronic occupation was already used by Vikram Gabini, my friend, to get the Gordon Bell Prize in 2 years ago. So that's we are kind of doing similar. And then the third level of divide-conquer-recombine is so-called a local non-local split operator. So to time propagate the electronic wave function, we need to do this repropagator. Then to effectively perform this, we refactor the electronic Hamiltonian into local part and then non-local part. So as I already said, at the bottom level, by using so-called a finite different basis, the local operation is the data pair, so it's a vector operation. On the other hand, for non-local correction is more global. So we switch the representation from finite difference to orbital base. So basically like an orbital, like a Hamiltonian interaction. That's the dense matrix. So that's the tensor computation. And then so this is a local vector and then non-local tensor computation split. In our so-called local non-local split operator approach, see, local part actually is nonlinear. That means the operator depends on itself, the wave function itself. So we need to use something called a self-consistent propagation. But more interesting is this, the non-local correction is actually perturbatively small. And also we use that the leading energy time is reproduced exactly. So that even afford that even lower pressure. So we use a hybrid FP32 and then BF16. So BF16 matrix multiplication accumulated with FP32 gem.
Well, and question, this is specifically for the interaction between the two models, that it can be approximated with low precision, not the computation, or also the computation.
Yeah, this computation. So this is, the idea is something important, but this something is small. And then which we use, physicists use something called the perturbation. So we have a kind of like a zeroth order or first order, like a kind of more or less accurate, but not like too much precise. But then we use perturbation. Perturbation is usually like a matrix multiplication. But the perturbation is already just a collection, so the dynamic range is small. So for physicists, this is kind of no-brainer to do.
So then one more question. This is something we're actually having an offline chat concurrently, trying to understand how, like computationally, how different is this calculation from a more Newtonian, like electrons, regular MD is just a Newtonian calculation. You ignore quantum. And you're not doing Schrödinger equation explicitly, but we're trying to get how much of the quantum interactions and what's it called, non-locality you have to put into these calculations to get the accuracy.
Yeah. So first of all, we are resolving all the wave function. Like each wave function could be 100 cube.
That was the core of the question. Yeah. Okay.
Yeah. So we are doing that honest quantum mechanics.
Okay, and that's a lot of the complication that it's because you have to deal with the whole wave function. You have to just approximate. In fact, maybe that's a good question. What about it can you ignore or you can approximate away?
So that's the so this is really the discipline of this the physical chemistry computer simulation people, the year by year we have like a new approximation method to more accurately represent things. So even the one slide you can see many recent papers based on. So to fully explain, we really need to go to this nitty-gritty of this physical chemistry in the community.
So I think what we're getting at as non-experts, actually, Ravi's asking is like you're capturing entanglement and quantum stuff, and it really is truly very high dimensional. You know, it's an infinite dimensional Hamiltonian space. But in your domain, a lot of it goes to zero pretty quickly, and your job is to find where it's typically zero, so you can ignore it.
That's right. So this is interesting in our community. Kind of like the face value complexity, kind of like a formal complexity exponential, but somehow cheap method like a tensor composite, like the decomposition, like a low dimensional, like the approximation, low rank approximation work extremely well. So there's a puzzle. Why is that? And then looks like it's coming from physical data locality principle. But now at the end of this talk, I will talk about what if this intrinsically difficult entangle problem, what to do? And then the answer is we need to go to quantum computer.
Of course, got it.
Okay.
Thank you.
So it's coming. Thank you. That's a very exciting topic. So these algorithmic innovations are complemented by our implementation innovation. So first of all, we use the open programming because we have an Intel GPU, but we also try NVIDIA GPU and then AMD GPU. So we cannot use, for example, CUDA for a GPU programming. So we try to be open. So our open programming approach is portable across all the supercomputer existing now through the MPI for message passing, OpenMP for CPU multithreading, and then OpenMP target offload for GPU offloading, and then neural net part is the PyTorch. And then in addition, we reuse the spatial stencil operator for this finite difference for an array of electronic wave function. It's called the structure of array, SOA, along with the blocking of the data for cache utilization, and then hierarchical parallelization over teams of thread and then thread on the GPU. And also our shadow dynamics metamodel-space-algebra makes large electronic wave function to be GPU resident. And then therefore, there's no CPU, GPU data center of the big data, which is facilitated by our custom OpenMP target data allocator destructor and to each program. So, so now we use also parameterized mixed precision computation through class template with for FP64 quantum excitation molecular dynamics, FP32 local field dynamics to compute small changes in occupation number. And then hybrid FP32 accumulation, the BF16, either 1, 2, 3, depending on the particular problem instance, matrix multiplication to compute perturbatively small non-local correction in LFD. So this is an example. So local Hamiltonian part by using data and then loop reordering, data blocking and tiling, and then hierarchical like team and then thread parallelization, we achieve like order magnitude speed up over the baseline. On the other hand, the non-local correction, as I explained, we switch the representation from finite difference to Kohn-Sham orbital to make that this correction dense complex matrix multiplication. And then, so what we can see is by using and then bigger problem size, we get the higher and then higher percentage of the spherical peak performance. The best performance we got is with hybrid FP32 BF16 and then 80% of the peak performance. And this is largely due to this the gemified the non-local correction as shown here. So by combining all of this, we broke the exaflop barrier. So using 16,000 GPU of Aurora, we achieved 1.87 exaflop. And then we also achieved nearly perfect parallel efficiency on this computer. Actually, another pillar of that our multiscale light matter dynamic is the excited state neural network quantum molecular dynamics, for which we also achieve like a 1.2 trillion atom, like a neural network quantum molecular dynamics. We also achieve nearly perfect parallel efficiency due to divide and conquer. So in our multiscale approach, the excited states neural network quantum molecular dynamics learn the excited energy landscape of the DC-MESH non-adiabatic quantum molecular dynamics. We have been pursuing this for several years. Regarding the neural network quantum molecular dynamics, we use the Allegro model developed by Boris Kozinski's group at Harvard. And then Allegro achieved the state-of-the-art accuracy and then speed founded on group theoretical equivariance and then local descriptor. So Allegro means fast. But on massively parallel computer like 60,000 GPU system, the growing number of unphysical force prediction, or we call the adversarial force prediction, prohibit simulation involving larger number of atoms for longer times due to a stochastic failure. So to solve so-called fidelity scaling problem, we developed Allegro legat method. Legat means smooth in music, and which use the sharpness-aware minimization to enhance the robustness of Allegro through improved smoothness. So kind of like a smaller Hessian of the cost landscape. So this elongate the time to failure. This is the time to failure as a function, the number of atoms in a log-log scale. So original Allegro failed very fast for larger system, but not Allegro legato. And this allowed us so-called a spectroscopically stable long-time Hamiltonian trajectory. And then with this, we are able to explain the state-of-the-art Newton scattering experiment at the Oak Ridge, kind of peak by peak using Allegro legato. The most recent development in here is Allegro foundation model. So of course, foundation models are paradigm shift in AI, where a single universal model acquires sufficient generalizability for diverse downstream tasks. So specifically, Allegro FM. Actually, this was developed by my colleague Kenichi Nomura, who is actually attending this meeting. So he can answer the detailed question of that. So his Allegro FM described many materials, properties, and processes covering 89 elements in the periodic table, and also exhibiting emergent capability like a fracture and then solid liquid dissolution, for which the model was never trained. So, so this is the second level of metamodel-space-algebra. So here, this universality was achieved by unifying large databases of multiple fidelity through the affine transformation, like a shift and then scale transformation in a metamodel space. So we have many approximation, quantum mechanical application, and then we unify this for the large data set. To do that, so metamodel space means the one axis is the level of theory, like a different approximation. The other is the kind of size of the data set. And then, so this is the kind of extrapolation. And this is how it was done in so-called multiscale simulation chemistry, which the Nobel Prize in 2013. So in this work, we even developed a so-called XS-NNQMD method, in which fine-tuned excited state non-neural network is added perturbatively to a pre-trained Allegro foundation model for ground state neural network. So again, perturbation. So this is really the heart of the multiscale QMM method, which is a topic of 2013 Nobel Chemistry Prize to my USC colleague, to Arya Varsha. And we are doing this for foundation model.
So this sounds important. So let me just poke on it. You're saying you're using the foundation model as a rough approximation, and then adjusting it using a real simulation as a kind of a bias correction process.
That's right. So this particular case, we kind of based on the ground state. So now excitation level, like without light is 0% excitation, and then with laser fluence, kind of like a higher and then higher excitation level. So neural network quantum molecular dynamics model is parameterized with that level of excitation. But also kind of delta machine learning.
Right, because I wanted to ask about this, because this is a form of mixed precision computation, where you say, I have a low precision algorithm, neural net, that can deal with bad hardware that's very fast, and it needs corrections from more expensive, unique, demanding algorithms like your QMD model.
Right.
Okay, interesting. Okay, cool. Thank you.
Yeah. So on Aurora, we simulated the laser-induced ultrafast dynamics of topological patterns in a prototypical so-called ferroelectric topotronics materials that lead titanium. So this included the photo switching of so-called skyrmion superlattice, that's a topological quantum entity. And then this movie is a photo-induced topological phase transition dynamic. And then, so this is similar to what is called a Kibu-Zurek mechanism in cosmology. Like it was supposed to be happening at the beginning of the universe. So what you can see is that the zoom in, zoom out. Let's play from the beginning. So this is a zoom out. So zoom into this atom level at the very small angstrom, and then we shine light now, and then that excite the electron, and then leftover is whole wave function, that isosurface. And then that ultra-fast attosecond motion in turn induce the topological changes. This is kind of ferroelectricity direction, the color-coded, and then that is propagating in many thousand angstrom. So in fact, a similar topological dynamics, light-induced topological dynamics, was observed in the experimental breakthrough using X-ray free electron laser at Stanford, using a linear coherent light source. And then So actually, we have been collaborating with LCLS, with NAQMD in a long, long time. And then this is the new addition. So this topological quantum matter holds key to sustainable society with ubiquitous and then power-hungry AI. And then by enabling ultra-low power transistor and then robust quantum computer. This is a topic of the 2016 Nobel Physics Prize. An example is the so-called attojoule switching logic element, which is again many order magnitude, low power consumption. So why we care? That we care because of you. And then we have an exponential growth of energy demand for AI computing data centers. And that is not sustainable because the energy supply is only growing linearly. This linear growth of that energy supply is already a problem because it comes with the cost of that additional CO2 emission. So we are supposed to be reducing the CO2 emission, but because of AI, like power demand, we are increasing. So who will power our future AI computing without burning out the Earth? And then this topological quantum matter and then quantum computer may be the answer. In fact, we simulated the non-trivial quantum dynamics on quantum computer, for example, to study ultrafast control of emergent magnetism by terahertz radiation in 2D material like this. Most recently, we simulated the surface mode in topological insulator using to mitigate noise. So this is what is using the quantum computer, topological quantum computer like a Microsoft. So our DCR MSA framework allows exponentially hard topological quantum many-body dynamics to be offloaded from Exaflop supercomputer to quantum processing unit. So this is what IBM is promoting, quantum-centric supercomputing. But I would like to discuss more with Google's quantum team to do some hybrid post-exascale and then quantum computing.
So actually,
yes,
this, because this is still too new for most of us to understand properly. Where in this problem is quantum computing appropriate? Because I mean, you've decomposed down the true quantum into so many smaller approximations. You've kind of simplified it away. Where within that space is full quantum computing constructive?
Yeah. So this is kind of like the entanglement. So somehow in most of the materials we deal with semiconductor insulator and then we simulate that the entanglement doesn't extend over like any significant the length scale. So that's why this is a quantum nearsightedness. But there are inherently like entangled quantum system, like extending large system. And then, for example, simple example, superconductivity is one example. So you can achieve macroscopic quantum like the coherence and then like entanglement at the device scale. So that was this year's Nobel Physics Prize. But that has to be very low temperature. So it's not trivial, but there are inherently complex quantum problems. And then for which quantum computer are the best solution. But honestly, most of the material science, we don't need that. But so some specialized entangled problem will need quantum computer. So actually, all the smart people, the quantum physicists, are squeeze in their brain. What is that killer application of the quantum computer? Still, we are struggling to find that the nail to hit with this the hammer.
Right. Thank you.
Yeah, thank you. So I want to finish with this question. Now what? So what does it mean to understand at the age of AI-assisted science? AI kind of give answer with a black box, and then are we understanding? To address this issue, next month we are starting new $4 million collaboration. So this is a collaboration between cosmology and computer science, like me, and also USC is the world famous cinematic art and then also philosophy department. So this is called the growing universe from quantum scales, discovery at the intersection of cosmology, epistemology, and then interactive visual media. So here, the philosophy epistemology is what do we mean to understand, and then that's the topic. And then it's kind of, I'm excited with this. So this is basically combined that like a high energy physics to study that dark matter. And then I'll be happy to introduce my colleagues who does this cosmology part to you in future. So in conclusion, regarding the paradigm shift, our divide-conquer-recombine and the metamodel-space-algebra paradigm solved the multiscale, multiphysics, heterogeneity, and low precision challenge, and thereby providing so-called a metascalable algorithm hardware co-design pathway at the nexus of post-exascale computing, quantum computing, and then AI. And then we broke the multi-exaflop barrier with that. And then while we use this approach to simulate the photo-induced switching of topological quantum matter toward the future ultrafast petahertz and the ultra-low power attojoule electronics, but this paradigm is actually applicable to broad multi-scale simulation and the modeling of complex systems, as represented by this several Nobel Prizes. With that, let me finish, and thank you very much for your attention.
Well, fantastic. Thank you very much. So one question that came in the call is error propagation. It seems like a lot of you're dancing with error right now. So to what extent do you have error propagation? How do you track it? How does it flow across different numerical precisions?
So that's good. So really this error correction is the big thing, and I'm not the expert, but I have a colleague, the Daniel Leader, that's a world famous in quantum correction. So it's really like these quantum physicists are doing quantum correction, but we are just using that error corrected the qubit. And then our latest work is interesting. The topological quantum dynamics, so like a electronic wave function is the topological. So it kind of the ball is genus 0, and then the donut is 1. So that topology is an integer. So you cannot, by thermal noise, switch from 0 to 1 easily. So that's why topological quantum matter is protected from thermal noise. And then that was used by Microsoft to do this kind of Majorana the quantum computer. But for us, we simulated the topologically protected dynamics. And then we show that even this noisy the qubit, we can simulate because that problem is good. So anyway, so this is the frontier, and then certainly without that error correction, we cannot do anything. But I'm not the specialist on that.
Oh, but then for leading your work, the numerical error correction, because a lot of the stuff you presented earlier, the approximation error is everywhere that you have to kind of tame it.
Right. So somehow we need to. So that's like a divide and conquer recombine. So it's like why that Arya got the Nobel Prize, because you just said divide and conquer.
Right.
But enzymic reaction is happening in protein that we do quantum mechanics. Who care like all the protein that outside, and then do molecular mechanics. So scientists have to really be. It's not the kind of black box and then just like apply that the most accurate thing everywhere. So that's a kind of like as a physicist, that's what I learned. If you cannot approximate, you are not physicist.
So then let me expand upon this. A lot of what neural nets do is they are dynamic approximators. They say, well, here's the neural embedding of this complicated state into the small dimensional vector. Nobody knows what it means, but it's a good approximation, I swear, and do something with it. To what extent is that usable? Because it does not have numerical properties, but it is in fact a good dynamic, approximation of the observed dynamics.
That's interesting. So the quantum chemists are finding this the exponentially complex quantum chemistry can be simulated by so-called the tensor network, and physicists call it the renormalization group in an order n manner. So that's a mystery. And then looks like the real physical system or chemical system using that's really like a small low rank subspace of that huge vector space. And then so that's the true, but and then quantum physicists are also interested in what are the intrinsically like entangled, that globally entangled. They call the entanglement entropy. That the large quantum, like that's inherently hard quantum problem. And then that looks like we haven't really understood what makes the quantum hard and then quantum easy.
Right. And so now a question online. Can you explain again how DCR1 accounts for long-range forces like Coulomb electrostatics?
Yeah. So so that's the kind of like the beauty of this Walter Korn's Nobel Prize and then density functional theory. So long range electrostatic interaction is treated with so-called a mean field approximation. All the electrons are like that individual and then kind of exponential combinatorics. But when you in a long distance, all this individual electron washed out, and then we look at the average electron density and then what electrostatic potential it creates. That we just need to solve one Poisson equation. And then that can be done with 3 hours. But then all this entanglement, many body correlation, that is the short range. And then that it is sitting in the domain by domain.
Right. So now pushing this further, because I'm going to go back towards neural nets. It does seem like I'm going to go for economics. Economics has mean field theory too. Yeah, my response depends on what the mean responses of everybody else around me, right. Except not everybody else, just my neighborhood in my social network, and then it starts getting messy. Like you have game theory involved. So to what extent are some of these? But it's not everybody's opinions that affect me. Just like a small, very weirdly structured shell around me. So to what extent is it feasible to use kind of these dynamic models that empirically learn these relationships and their dominant dynamics, physics and economics, same basic thing, without maybe difficult for us to understand exactly what they learned? How usable is that? And to what extent can we find a new theory we do understand from these adaptive approximations?
It's beyond my domain, electron out of human.
I know, but it's the same problem, it seems like, because you have your own crazy atoms and electrons that, in the average case, are not too bad, but sometimes they go crazy.
Yeah. So that yeah, I don't know. Maybe I'm not the expert, but I'm kind of as a physicist always interested in the kind of low rank approach. We cannot memorize everything, right? So somehow we are kind of like organizing our semantic network in a certain kind of, I don't know, certain like vector space we are forming there, and then that's a low rank, and then there may be something in there like we pursue this low rank approximation. That another thing my colleague is doing is something like a surprise. And then if you observe something and then we prototyping with low rank approximation, and then some observation come, it's a surprise. And then maybe it need to expand at another like a vector axis. So I don't know, that kind of like a mean field with adaptively like expanding, but whenever like something we cannot explain. That's what this philosophy, the collaboration. Yeah. And then we said AI is very good at like deduction and the induction logic, but what they cannot do well is that kind of discovery or like a hypothesis, come up with a crazy hypothesis that is called abduction. And abduction is not explained. How we can come up with this abduction suddenly by human brain? So probably that go to that direction. So anyway, probably later I want to introduce you to this new kind of cosmology, philosophy, and then computer science.
Yeah, no, that's exactly the questions I'm asking. Well, fantastic. I think, are there any more questions on the call? Actually, well, somebody's pointing out GNNs, and actually, I mean, graph neural networks are one way of dealing with this nearby interactions in a structured way, and it's like transformers are a way of doing graph neural networks in a way that just adapts to which way you're paying attention. So that might be a good way of structuring it.
So USC, like we are very big on the spike neural network. It's more like a brain, so like it's just a spike and then just dynamically reconfiguring this pathway. That's what I was talking to your employee, like Brandon is here, like this Google's what's called some future pathway to future AI future. So that's the thing, network, and then just kind of firing that the base path firing and then to do multitask. So I think that's the direction I see. Yeah, computer science, we said the sparsity is the key for low power consumption.
Right, and hopefully for summarizing the dynamics in every one of these domains.
Right. So cool. Yeah, so this is very exciting. This does not this a megawatt, but the kind of like a kilowatt the super brain or something.
Yeah. Well, cool. Yeah, thank you very much. It was a fascinating talk, and thank you for actually taking the extra time.
Yes, thank you for this very good question. Like, yeah.